All right, let's get started. Good afternoon, everybody. We will discuss a very interesting topic today, which is counting methods. Okay, so we will discuss what is permutation, what is combination, and in which situation we choose which method, and also what is conditionality. Okay. The fundamental principle of counting. So assume for experiment, we have k operations. So we have k steps. Okay. If for each step, we have n1 step to perform the first operation. And for each of these ways, there's n2 ways to perform the second steps, second operation, not calculation. That's typo here, and so on. Then the total number of ways to perform the whole sequence of k operation will be n1 times n2 ... times nk. So in other words, if we have k steps in a certain experiment, and for each steps we have certain ways, such as n1, n2, and n3, then the total number of ways to perform that sequence is n1 times 2 times nk. Okay. So that's the fundamental principle of counting. So if we toss a coin, we toss 3 coins, then the total number of simple events will be 2 times 2 times 2. So we toss 3 coins. So for each coin, there's 2 possible outcomes, head and tail. So the total number of the 3 coins being tossed is 2 times 2, so totally 8 steps. If we toss 2 dice, the total number of simple events will be 6 times 6. For each die, we have 6 possible outcomes. So 6 times 6, 36. Okay. We have 2 candies drawn from a dish. So in a dish, we have 2 red candy and 2 blue candy. So the total number of simple events will be 4 times 3. Okay. So we have 2 picks. First time we pick 1 candy from the dish, which has 4 candies. So the number of possible outcomes for the first step is 4. After the first pick, we have 3 candy remaining in the dish. Okay. So the second step, we have 3 choice. So that is 4 times 3. Another example. So when ordering a certain type of computer, there are 3 choices for hard drive. We have 4 choices for memory, 2 choices for video card, and 3 choices of monitor. So how many ways computer can be ordered? Okay, so we think ordering a computer as experiment. To finish that experiment, we have 1, 2, 3, 4 steps. So the first step, so we choose a hard drive. How many ways? 3. So 3 times the second step. The second step, we choose the memory, which we have 4 choices. So that's 3 times 4, and similarly times 2 for video card, and times 3 for monitor. So how many ways? So we have 3 times 4 times 2 times 3. Okay, so that's the general idea of counting method. So simple enough. Then let's look at this example. Okay, and we will introduce the idea of permutations. So we have 5 lifeguards available for duty. There are 3 lifeguard stations. Okay. The question didn't tell us the 3 lifeguard stations are the same. So we assume they are different stations. Okay. So in how many ways can the 3 lifeguards be chosen and ordered among the 3 stations? Okay. Okay. So similar to the last question, we can think this experiment as 3 steps. So let me just share my notes with you. Okay, here's the question. 72. The answer. So let's see. So we have 5 lifeguards. Okay. 5 persons. And we have 3 stations. Okay, 3 stations. Let's call it 1, 2, 3. So we need to choose 3 lifeguards and we need to assign 1 lifeguard for each of the 3 stations. Okay. So the first step, we need to choose, 1 lifeguard for the station number 1. Okay. So station number 1. And because we have 5 lifeguards, we have 5 ways. Okay. And second step, we need to choose a lifeguard for the station number 2. Okay. Because 1 lifeguard already chosen, we have 4 remaining lifeguards. So we have 4 possible ways for the second step. For the third step, station number 3, and we have 3 lifeguards remaining. So that is how we come up with this. So 5 times 4 times 3. So that's counting method. So 60 ways to do that. In general, we can use, for this kind of question, we can use the equation of permutation to calculate. Okay. So permutation is called P. Okay. So PKN means in this question, we try to pick 3 lifeguards from a total 5 for the 3 stations. Okay. So we can simply use equation P35, okay, which is shows here. Okay, so PNK is equal to, this is factorial of n. Okay, so factorial of n will simply be n times n minus 1 times n minus 2 times 3, 2, and 1. Okay, so as we can see from here, so that is factorial of n divided by factorial of n minus k. Okay. So P35 will be factorial of 5 divided by factorial of 5 minus 3. Okay, right, so that will be 5 times 4, 3, 2, and 1 This will be 2 times 1. Okay, so simplify that will be 4, 5, 4, and 3. So that's 60. Right, so that's the equation for permutation. So permutation is the ordering of a collection of objects, similar to we assign lifeguard in the 3 stations. Okay. The number of permutation of n object is factorial of n, okay, and which is equal to this. And of course, factorial of 0 is not 0, it's 1. So that's a special case. The number of permutations of k objects choosing from a group of n objects, such as we choose 3 lifeguard from the 5 lifeguard for the 3 station. So we use equation for permutation of this. Okay. Here is a very important notes. Okay. So when order matters, use permutation. So what does this mean? In the lifeguard example, so we choose 3 lifeguard and we assign them to 3 different stations. Okay. So in this case, the order doesn't matter, okay, because the stations are different. So this is when the order matters, we should use permutation, which is PKN. In this example, is P3, 5. In other situations, when the order does not matter, okay, then we should use a new equation, which is called combination. Okay, as you can probably guess already. So we have permutation and then we have combination. So 2 sets of equations. When order matters, we use permutation. When order does not matter, then we use equation of combinations. Okay, and in this example, the order does matter. If we say, we choose 3 lifeguard from this 5 lifeguard, and then let's say, okay, the order doesn't matter. We do not assign the 3 lifeguard to 3 different stations. We just pick 3 lifeguard from the total 5 lifeguards. In that case, the order does not matter. Then we should use equation for combination instead. Okay. So we'll look at that in a moment. Before we do that, here's another example of permutation, P. Okay. So a lock consists of 5 parts and can be assembled in any order. Engineer want to test each order for efficiency of assembling. How many orders are there? Okay. So we can assemble 5 cards in any order. Again, we think this work as an experiment, which has 5 steps. Okay, so we have 5 parts. We call that P1, P2, P3, P4, P5. Okay, and the first step, again, we choose 1 part for the step number 1. Step number 1, we choose 1, which of course we have 5. And step 2, we have remaining 4 parts left. So we have 4 choices and so on. Okay, so this is an example of permutation. And we should use P and K. In our case, we need to choose 5 from the total 5. So here N is 5 and K is also 5. So P5, 5. Okay, so 5 minus 5 is equal to 0. And factorial of 0 is equal to 1. So that's how we get 120 weights. So that is introduction for permutation. Any questions before we move on to combination? Okay. Combination. So considering permutation of 3 of the letters, okay, so we choose 3 letters from the 5, A, B, C, D, and E, okay, and in this case, this is all the possible outcomes when ordered matter. So the first letter we choose, could be A. Could be B. Okay, so that will be P3, 5. So we pick 3 from the total 5 letters. Okay, so P3, 5 will be factorial of 5 times factorial of 5 minus 3. So we have a totally 60. Okay, so that's here a total of 6 different ways. Combination are unordered collection of objects. So let's say we just pick 3 letters from A, B, C, D, and E from these 5. And the order of these 3 does not matter. Okay. Then we should use combination, which is C and K. C and K. The number of combination of K objects chosen from group of N objects, okay, such as CEE305, okay, will be calculated using combination equation here. So C is for combination. And look at the equation here for combination is similar to permutation. Okay. In fact, this part is PKN, right? So we can write CKN in another way, which is PKN divided by factor of K. So we can see from here clearly, for combination, it has less possible ways compared to permutation because it's divided by factor of K. And here shows the special situation, which we'll touch in a moment later today. So the number of ways to divide a group of N objects into R groups, K1, K2, KR. Okay, and K1 plus K2 plus plus KR is equal to the N objects. Okay. Then number of ways to do that, we can use this special equation. Okay. Here's another example for combination. Right. So 3 members of a 5-person committee must be chosen to form a subcommittee. How many ways? Okay, so we choose 3 from 5, similar to a lifeguard situation. But here we just choose 3 members and form a subcommittee. The 3 members, the order of them among them does not matter. The order again does not matter. Then we use combination. We use CEE305. Right? Plug in the equation number. So N is 5, K is 3. So N minus K is 5 minus 3. We have 10 different ways. For P35, we have 60 ways. Okay. So combination, we have much less ways to do that. Okay. Again, the order of choice is not important. We use combination. So if, let's say we choose 3 members of a 5-person committee and form a subcommittee, okay? And in this subcommittee, the 3 members have different roles. So for example, we have president, vice president, VP, and secretary. Okay, so we choose 3 persons from the 5%, and then we assign them to different roles, 3 different roles. In this case, we should use permutation because the order does matter in this case. Okay, so that's the difference between combination and permutation. Okay. Another lifeguard problem. So we have 6 lifeguard. So 6 lifeguard available for duty. There are 3 lifeguard stations. How many ways can be chosen? Okay, question tells us without regard to their order. So without regard to their order, combination. Okay, so C and KN, we need to choose 3 lifeguard from a total 6. Okay, so that will be factor of 6, factor of 3, 6 minus 3, factor. Okay, so we have 20 ways to do that. So this question tells us clearly the order does not matter. But sometimes the question does not tell us. We need to figure out whether to use combination or permutation. Okay. In this example, in certain event, we have 30 people and 5 will be chosen. Also, the question tells us nicely, order does not matter. The order does not matter. So combination then. So we choose 5 from 30. Okay, so that will be equal to a factor of 30. 30 minus 5 factor times factor of 5. Okay, so you can calculate how many ways. So next question. Okay, in this question is we're gonna use the special equation here. Okay. So number of ways to divide a group of n subject into R groups, and the number for each group added together is equal to n. Okay, so that's number of ways to do that. So we have a die rolled it 20 times. Okay, so 20 times, and for this 20 times, 3 times the upper face shows 1. 5 times the upper face shows 2. 4 times 3, 2 times 4, 3 times shows 5, 3 times shows 6. Okay, so we roll a die 20 times, and this is the number of times for each number, 1 to 6. So how many different arrangements of the outcome are there? Okay, so we use the special equation here. The totally n is 20. Okay, but for all the possible outcomes, we have k1 ways for number 1, k2 ways, and we have k6. Okay, so n is equal to 20. So we have 3 times we have number 1. So that will be 3 factorial of 3 times 4 times we come up with number 3. So that is factorial of, no, sorry, 5 times come up with number 2. That's factorial of 5 times 4 times come the 3, factorial of 4 times twice shows a 4. So that's factorial of 2 times 3 times come up with 5. So it's factorial of 3. And finally, 3 times come up with a 6. So that's factorial of 3. Okay. So how many different ways we can calculate? During the test, you can easily use your calculator to do this kind of calculation. You don't need to expand that. So the final answer for this question is so this much. So 1.955 times 10 to the power of 12 ways. Okay. Great. Any questions or comments before we look at the next question? All right, so the next question is still about candies. So a box of 6 candies, as we can see here, we have 4 red and 2 green. Child select 2 candies. Okay, so that's 2 picks, 2 steps. What is the probability that exactly 1 is red? Okay, so the child select 2 candies out of the 6, but which one is the first pick, which one is second pick, doesn't really matter. So the order of choice is not important here. Okay, we only care about the color. So that is combination question. We should use CEE305. We choose 2 candy from a total 6 possible. Okay. After calculation, we found out we have 15 ways to choose 2 candy out of 6 candies. Okay. So one way to resolve this question is shown here. So number of ways to choose 1 green M&M candy, because in the box we have 2 green candy here. Right? So number of ways to choose 1 green is C12. Okay, we choose 1 green from the 2 green candies. Right? So C12 is 2. Okay. And similarly, the number of ways to choose 1 red M&M candy is C14, because we have 4 red candy. So we have 4 ways to do that. So totally we have 4 times 2, or 8 ways to choose 1 red and 1 green. And in total, we have 15 ways. Choose 2 from number 6. So exactly 1 red. The probability for that is 8 divided by 15. Okay. So that's one way to resolve the question. There's another way. Out of the 15 total ways, okay, so the 15 total ways, how many possible color combinations we have, right? So we only have 2 colors, red and green, right? So we could have 2 red candy, right? We could also have 2 green candy, or we could have 1 red and 1 green, okay, which is the question is asking. So exactly 1 is red is equal to 1 green and 1 red. So that is what the question is asking. And for 2 red, how many ways? Okay, we have 4 red candy. We choose 2, and the order does not matter. So that is CEE305, which is equal to 6. How many ways we have 2 green candy? Okay, we only have 2 green candies. So we choose 2 from 2. So that will be CEE302, which turn out to be 1. Okay. And then the remaining possible ways will be 1 green and 1 red. It is 8 ways, as we can see from the method we just discussed. Or we can use, we know the total way is 15. So that will be 15 minus 6 minus 1. So 6 is number of ways we have 2 red, and 1 is number of ways we have 2 green. So that is also equal to 8. So 8 over 15. Okay. All right. So far we have discussed when to use combination, when to use permutation. Remember, when order does matter, use permutation. Does not matter, we use combination. Then let's look at conditional probability. First, let's review the previous example. So this is the 1,000 rod and the specs for the rod. Okay, the length of the rod could be too short, too long, or okay. The diameter could be too thin, too thick, or okay. Okay, out of 1,000, so this is allocation of number of rod for each requirements. And what is the probability that the rod is too long? Okay, the rod is too long will include 3 situations. Okay, so we have 2 rod, which is too long and too thin. Okay, too long and too thin. We have 25 rod, which is too long, but the diameter is okay. And then we have 13 rod, which is too long, but the diameter is too thick. So what is the probability that the rod is too long? It will be, we add number together, 2 plus 25 plus 13, divided by the total number of rods, which is 1,000. So the probability that a randomly chosen rod is too long will be this. Okay. So we discussed this last time. The second question, would your answer change if you already know that the rod is too thick? Okay. So the condition here is before we calculate the probability, we know the rod is already too thick. Okay. It's already too thick. Let me look at here. This is too thick. If we know the rod is already too thick, that's only 5 plus 4 plus 13. So this is the number of rod is too thick. And this is the condition. Okay. So if you know the rod is already too thick, then what is the probability is too long? Okay. So anybody want to have a guess? How many rods are too thick? 5 plus 4 plus 13. So that is equal to 22. Okay. So under this 22, within this 22, how many rods are too long? Under this 22, how many rods are too long? 13, right? 13 is too long. So the answer will change if we already know the rod is too thick, what is probability is too long. So P too long under the condition we write as a line. Okay, so this is given or under the condition it is too thick. Okay, so that's the probability will be 22, too long is 13. Okay, so that is idea of conditional probability. Okay, the answer will be different, actually quite different compared with the first part. And let's look at section 2.3, talking about conditional probability and independence. Definition, probability that is based on part of the sample space is called the conditional probability, such as the condition is the rod is too thick. Then part of the sample space will be 22, 5 plus 4 plus 13. Okay. And how we can write conditional probability? We use here. So probability of A given B. So this line simply means given. It's not divided by B. Okay, given just means probability of A given the condition of B is equal to this. Okay, and provided event PB is not equal to 0, so that is PA half circle facing down is AND or intersection. So this part is A and B or intersection. Sorry for the handwriting. Over PB, over PB. Right. So if we draw a diagram, we call that a Venn diagram. For circle A and circle B, and intersection of A and B, we know is here, right? So the intersection will be on the top, and PB will be this circle B. Okay. This is another example we discussed last time. So about effects on aluminum cans. So manufacture aluminum cans. The probability a can has a floor on its side is 2%, and the probability a can has a floor on the top is 3%. Probability has a floor on both the side and top is 1%. It's 1%. Okay. Again, sometimes it's easier to see the relationship if we draw the Venn diagram like this. So let's say this is the property has a floor on the side S, and this is has a floor on the top T. We call that T top. Side. Okay. Question tells us the property can have floor on the side is 0.02. Okay, so this circle is 0.02. Property has a floor on the top is 0.03. So this circle is 0.03, and have a floor on both the side and the top is 0.01. Okay, so that means here the intersection intersection means both A and B, both side and top. So this part is 0.01. Okay. The diagram is not drawn proportionally, but we can simply calculate the probability on other area, such as the probability the can has a floor on the side, but not on the top. On the side, but not on the top will be here, right? So inside the circle of side, but outside the top. Okay, so it will be simply equal to the whole circle, which is 0.02 minus intersection 0.01. Okay, and so on. We can also calculate the property here, which is the chance it has a floor on the top, but not on the side. Okay, and that part will be the whole circle 0.03 minus the intersection 0.01. Okay. Or we can use the equation here, P A given B. Okay. So P, the question is asking here, what is the probability that a can will have a floor on the side, given that it has a floor on the top? Okay. So that is a P S given top. Okay, this will mean the probability of floor on the side S, given the condition is this line. Again, this line simply means given the condition. It's not divided. It's not S divided by T. It's S given by condition of T. Okay, so given has a floor on the top. Using the equation in the previous slide, it will be P S and T over PT. Okay, so we use the equation here. Okay, PS and T will be the intersection, right? Intersection is here, 0.01. And PT will be this part, 0.03. So that's conditional probability. So given that it has a floor on the top, means we limited the situation within that circle, which is has a floor on the top. We know that already. That's a condition. Again, PA given B is equal to PA and B times PB. Okay, so PB is the circle of B is here, and PA given and B will be the intersection, shaded area. Okay, so from here, you know how to calculate conditional probability. All right, so any comments or questions? You want me to repeat anything before we continue? All right. So independence, we touched this idea before, independence. If two events A and B are independent, if the probability of each event remain the same, whether or not the other occurs. Okay. If A, PA, and PB not equal to 0, okay, we can conclude A and B are independent if we know this is PB given A. Okay. So the condition is A. What is the probability? That's PB given A. If PB given A is equal to PB, or PA given B is equal to PA, then these two events are independent. If either PA or PB equal to 0, then A and B are also independent. Okay. If we have more than two independent two events, A1, A2, and AN, if the property of each remaining the same, no matter which the other occurs, then we also call this n events independent. Okay. Then we can check if two events are independent or not. For example, if we toss the coin twice, okay, so if event A is defined as we have a head on the second toss, event B is we have a head on the first toss. Okay, so first let's just figure out using counting method what are all the possible outcomes, what are the chance for each of the possible outcomes. Okay, so first pick, first toss. Okay, we could have head or tail. Okay, head or tail. And then for the second, for each of the head and tail, we could also have head or tail. Okay, so we have 4 possible outcomes: head, 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 tail, tail, head, and tail, tail. Okay, and they are equally likely events. So each of these 4 outcomes, they have 25%. Okay, all right. So let's check if event A and B are independent. Okay, so PA given B. Okay, given B, what is B? B is we have a head on the first toss. Head on the first toss is here. First toss we have head. So these two belong to B. Okay, so PA, what is PA? PA is we have head on the second toss. Okay, we have head on the second toss, which is here, head, head. So that's 25%. So PA given B will be 1/4 divided by PB, which is the first two events here, so 1/4 plus 1/4. So that's 1/2. Okay. And also we check what is PA given not B. Okay. Given not B is the head is not on the first toss, which means the first toss we have tail, which is this two. This two is not B. Okay. Again, after calculation, PA is we have head on the second toss, which is here. Same thing. We have 1/4 divided by 1/4 plus 1/4 is 50. Okay. So after calculation, we found out PA does not change whether B happens or not, okay, because they all equal to 50%. So these two events, A and B, are independent. And here shows two events are not independent. Okay, again, we use the candy problem. So we have 5 candy, we have a 3 green, a 3 blue, sorry, and 2 red. So choose 2 candy at random. A is the second candy is red. Okay, so B is the first candy is blue. All right. So then let's calculate PA given B. Okay. So PA given B, what is B? So B is the first candy is blue. All right. So the first candy is blue. So let's see, we get blue already. So for the second pick, we have 2 blue and 2 red remaining. So the probability of the second candy is red, given the first pick is blue, will be 2/4, right? We have 2 red out of the 4 candy. So 2/4, that's 50%. What is PA not B, given not B? So not B means the first candy is not blue. Then the first candy will be red then. Okay, we only have 2 colors. Not blue must be red. Okay, that means the first pick is red. So before we do the second pick, we have 3 green, blue, three blue and 1 red. So the chance for the second pick is red will be 1/4 then. Okay. So A does change depending on the B sort count. So A and B in this case are dependent. Okay, so that's the idea of dependence events. Okay. So this is called the multiplication rule. It's similar to the conditional probability, as you can see. So if A and B are 2 events and PB not equal to 0, then this is the PA and B is equal to PA given B times PB. So this is the same as the conditional probability. PA given B equal to PA and B divided by PB, right? So this is what we just discussed several slides before. This is conditional probability. If we move PB from bottom to the left side, it will become this equation. So tells us the same thing. Okay. And similarly, if PA is not equal to 0, this one also holds true. If PA and PB both not equal to 0, then both these 2 equations above holds true. For 2 independent events, A and B, PA and B will equal to PA times PB. Okay, such as we toss the coin 2 times. So the 2 toss will be independent to each other. Right. So this is called the multiplication rule. If we have more than 2 independent events, then this one also holds true. Okay, we have n independent results. Okay. And for each collection of AGI, AGM of events, then the probability of AGI, this is again and, okay, will equal to PAGI times PAJ2. Okay. And more often, if n events are independent to each other, okay, this equation holds true. Okay, it's PA1 and A2 and AN equal to the probability of each timed together, such as we roll a die or toss a coin. Okay. They are independent events, then we can use this equation. All right, enough equations. Let's look at some questions. So here shows microprocessors manufactured by certain process. Okay, 20% are defective. Okay. Then 80% are not defective. And then we have 5 microprocessors chosen at random. And tells us they are independent. What is the property that they all work? Okay. So because these 5 microprocessors are independent to each other, so we can use multiplication rule. So the probability of all work will be equal to the first one work, okay, and the second one work. And the fifth one work. And because they are independent to each other, so it will become a property of the first one work times the property the second one work and the property the fifth one work. Okay. The question tells us 20% is not working. Then remaining 80% will be working. So that's 0.8 times to the power of 5. Okay. All right, so we're almost there for today. The same question, RB asking, what is the probability that at least one works? Okay, so that will be more complicated. So at least one work. So at least one work, including because we have 5 total. At least one means we have 1 work, or we have 2 work, 3 work, 4 work, or all 5 works. Okay, so we can calculate the probability of all these 4 and add them together. Okay, or we can use a common trick, which will be touched many times in this semester. At least one work is also equal to 1 minus the probability 0 work, none work. Right, and that would be much easier to calculate. So 1 minus probability of none work will be equal to at least 1 work. Okay. So the probability of at least 1 work. Okay. So this part, the probability of none work, because again, this is 5 independent steps. So the probability of none work will be probability the first not work, NW, times probably the second not work, the fifth not work. Okay, will be equal to 20% to the power of 5. To the power of 5. So the final slides today tell us how to decide when events are independent. Okay, so the best way is to think carefully the process of that question. We think that question as the experiment, and that experiment has certain steps. Okay. For example, if a coin is flipped twice, then of course, the outcome of the second flip will be unaffected by the outcome of the first. Okay. The second example, it is reasonable to expect that number of people attending the sport event is depend on the ranking of the visiting team. Okay, so that is the common sense. Sometimes we use common sense to say 2 events. In this case, 1 event is the number of people attending the event, sports event. The second will be the ranking of visiting team. So these 2 things are dependent to each other. Okay. Or in this situation, depending on the number of items from the sample, we discussed that before. The item in a random sample may be treated as independent unless the population is less than, is small enough, which means the sample size is more than 5% of the whole population. Okay. Remember in the previous lecture, we talked two examples. Okay. So one is we have 2A and 2Bs. The other one is we have 1 million A's and 1 million B. Okay. Right. We pick two from each of these two cases. Okay. In this case, because the population is so small, okay, the second peak is depending on the result of the first peak. For example, if the first peak is A, the second peak we get A will be 1/3. If the first peak is B, then the second peak we get A will be 2/3. So these two peaks will be dependent on each other. But if we have more than enough population, so this is the rule, 5%. If the sample size is more than 5% of the whole population, then the peaks will not be dependent. If the population is large enough, then the first peak will be independent to the second peak. All right. So the next is talking about the law of total probability. I will save it next time. So see you on Tuesday next week. Remember, we still do online teaching next week, and then from February 1st, we'll see you in person. So any questions?